Alright, today we're going to take a look at the mathematical relationship correlation between equilibrium and its position. For any type of equilibrium reaction, we always have the double arrow where, in this case, these lowercase letters represent the number of moles and the uppercase letters represent the species, either the reactants or the products. KQ is a value that's calculated, that is a constant, and the KQ value is specific for a specific temperature. When we write an equilibrium expression, KQ is the constant that you're trying to calculate. And how do you calculate it? It's the concentration of products multiplied by the power of the number of moles divided by the concentrations of the reactants to the power of their number of moles. Solids and liquids are not included in the expression because their concentrations are constant. So when we are given a solid or a liquid in a reaction, we're just going to simply replace it with the number 1. Chemists have described a mathematical expression of Le Chatelier's principle that allows them to predict the exact concentrations of substances in the equilibrium when shifts in concentration, temperature, and pressure are made. That is the equilibrium expression. That is KEQ. This expression allows chemists to use chemical equilibrium in large-scale settings to make predictions of expected products for certain equilibrium processes. The expression produces a constant value of any equilibrium at a specified temperature and pressure. Again, I'm going to underline this because KEQ is specific at a specific temperature and pressure. The size of KEQ gives a chemist a quick idea of the position of equilibrium. Is it on the reactant side or is it on the product side? Here's an equilibrium reaction above, and we're going to go ahead and write the equilibrium expression. It looks like this. KEQ equals the concentration of the products, which is NO2 raised to the power of 2, divided by the concentrations of the reactants, which in this case is the concentration of oxygen, times the concentration of nitrogen gas, both of which only have 1 mole each, so therefore it is just to the power of 1, and we don't have to write that when we write the equilibrium expression. Here's another type of example problem. Again, KEQ equals the concentration of CH3Cl multiplied by the concentration of HCl divided by the concentration of Cl2 multiplied by the concentration of CH4. Since all of these coefficients are 1, notice how nothing has an exponent. The magnitude of KEQ, again, varies only with temperature. In other words, it can change if you change the temperature. But if the temperature remains the same, it remains constant. It's independent of initial concentrations. In other words, you can change the concentrations and the KEQ value will stay the same. So let's take a look here. In our reaction, we have reactants and we have products. Notice how the concentration of reactants is larger than the concentration of products. So what does this tell us? This tells us at equilibrium, which is at this point right here, because the rates are the same, KEQ is probably going to be less than 1. Okay? The reason why is because when you do KEQ, it equals the products concentration divided by the reactants concentration. As you can see here, the products are less than the reactants, so therefore the answer is going to be less than 1. So what do these numbers actually mean? Well, if you have a KEQ greater than 1, you get mostly products. The way I remember that is this right here. This arrow is pointing in the direction of the products. When KEQ is less than 1, you get mostly reactants. In other words, the position of the equilibrium is on the reactant side. If you have KEQ roughly about 1, then you are at a point where you're not favoring the products and you're not favoring the reactants. You're somewhere in between. So KEQ is used to tell if a reaction will favor products or reactants. Here's another example. Okay, so we have nitrogen gas plus hydrogen gas makes ammonia. Okay, notice that this is a balanced equation. Here is our KEQ value, and our KEQ value is 3.5 times 10 to the 8th. So, will this tell us that the equilibrium position is at on the product side or on the reactant side? Okay, well, in this case, since the concentration of products is much greater than that of the reactants, because KEQ is greater than 1, therefore the position is at the product side. Here's another example. We have silver chloride, which is a solid, and we have aqueous silver ions and chloride ions in solution. And our KEQ value is 1.8 times 10 to the negative 5. So what does this tell us? Well, this tells us that the concentration of products is much less than that of the reactants at equilibrium. Therefore, the reaction is strongly favoring the reactant side. And this is exactly what we just did. Okay? So, KEQ, since it is less than 1, reactants are favored. However, if we do the reverse reaction, the products are therefore favored. Here's a reaction where you actually have to calculate KEQ. So, in this case, for the reaction, we have 2HI, which is a gas, goes to hydrogen gas plus iodine gas at 448 degrees Celsius. Do not be confused by the temperature. The temperature, again, is just there to let you know that we are at equilibrium at a certain temperature. Okay? So we want to find the KEQ given these numbers of concentrations. Okay, so we have 0.0040 molar of HI. We have 0.0075 molar of hydrogen gas, and we have 0.00043 molar of iodine gas. So, first step is always to set up an equilibrium expression. Okay? And we have KEQ equals concentration of I2 times the concentration of H2 divided by the concentration of HI to the second power. Since we have our equilibrium concentrations, we're going to go ahead and plug those in, and when we plug those in, we get a KEQ value of 0.020. So what does this tell us? This tells us that since KEQ is less than 1, we are on the reactant side. Or the reactants are favored. Here's another example. When the equilibrium is established in 5.00 liters container, equilibrium concentrations are nitrogen 3.01 moles, hydrogen 2.10 moles, ammonia 0.565 moles. Calculate the KEQ. Well, we need to take an initial step in order to solve this problem. And the initial step is that you need to convert to concentrations. Well, we have moles and we have liters, so simply we're just going to take the number of moles and divide it by the total liter of the container. And we get these values. Now we're ready to calculate KEQ. When we plug them into our equilibrium expression, which is the concentration of NH3 to the second power, divided by the concentration of N2 times the concentration of H2 cubed, we get this expression and we get this answer to 3 significant figures. Now again, what does this tell us? This tells us that the equilibrium is favoring the reactants. Why? Because KEQ is less than 1. All right, last thing that we're going to do is we can use KEQ to find equilibrium concentrations at that temperature. Okay, for example, for this reaction, we have N2 gas plus O2 gas goes to 2NO gas, and we have a KEQ value of 6.2 times 10 to the negative fourth. So this is telling us that we mostly have large concentrations of the reactants, because again, KEQ is less than 1. And again, it gives us a temperature. Don't be concerned about the temperature, because that's just telling us where we are at that specific temperature. The concentration of N2 and O2 are both 5.2 moles per liter. In other words, they are both 5.2 molar. Find the concentration of NO. All right, so first thing we do is we set up an equilibrium expression, and there it is. We have the concentration of NO squared divided by the concentration of N2 times the concentration of O2. We plug in our values, okay, and then we solve for the missing one. When we solve for the missing one, we get the concentration of NO to be 0.13 molar. Don't forget, since you have this squared, okay, in order to get rid of the square, you have to take the square root. All right, hope you guys found that helpful, and please let me know if you have questions in class. Thank you very much.